Okay, so hello everyone, welcome back. I'm certainly very glad to be back. I don't know if you are or not, hard to say. In an effort to say thank you for your patience, I did bring candy for the class, so feel free to grab a handful on your way out if you want it. So I thought what we would do for today is take a couple of minutes and review the schedule changes due to the strike, because there are some changes that I posted on Brightspace. We'll just take a quick review of all the things we've done so far, so just to bring some of those ideas back. I will let you ask all the questions you want. I may not know all the answers, but I'll give it my best shot or figure it out. Then after we do all that, we'll continue on and finish chapter 24. I did make a few edits to that chapter, so we'll kind of finish off from there. So first thing, schedule changes. I've posted this on Brightspace, and I will post it with the class notes as well. So one major change is the number of tests. I feel like I don't want to overburden you with testing, so I decided to cut back. We lost 2 tests over the strike, and rather than have kind of the remaining 4, I thought we'll bring that down to 2 more tests. I'm still going to drop your lowest 2 test grades, so that's still in the plan. Instead of having the test to be in 20 minutes followed by a lecture, I'm going to have the test take up the whole time in the class. One impact of that is if you get accommodations for time or other things from the Blunden Center, you should reach out to them and make sure those accommodations are in place before the test happens. I don't really want to give you a test the first week we're back from break, because I figure all your other profs are going to. So I bumped it to the week after that. So we'll have test number 4 on March the 10th, test number 5 on March the 25th, and then that'll be the last 2 tests for the semester. So that's my plan there. Some important dates to point out. April the 6th, it doesn't have any impact on this class, but it might matter to some of your other classes. That's going to follow a Tuesday schedule, right? So it's really a Thursday, but whatever you have on the go Tuesdays, that's what you're supposed to do on April the 6th. April the 7th is Good Friday, so that's not a day on campus, no classes there. April the 6th was originally the last day of classes, but they have added 1 additional day of classes. That's the April the 10th. So we are here Monday, April the 10th. So that'll be a last class. Then you get 2 entire study days before exams start. They'll start on April the 13th. I saw on one communication from the Senate that April the 15th, a Saturday, was also going to be an exam day. I haven't seen that widely publicized, so I don't know if they took it back, if they changed their minds. But regardless, keep an eye out for your exam schedule in case you need to make accommodations with your work or family structure or whatever. So that Saturday could end up being an exam day. Those are the big days. I don't have the lab information here on this. Because of our snow day on Wednesday, it had some implications for the lab schedule. Edward redid the lab schedule. He's got that up on Brightspace. I'm not going to reproduce it here because I'm afraid I'll get it wrong. So just keep an eye on that schedule. It mostly impacts the last couple of weeks of the course, some things being switched around. We will have ended up losing 7 classes with the snow day and the strike. It's not insignificant. So when I thought about what we had to do, I kind of felt like there's 3 options. I could go faster. So in class, I could try and talk faster and not answer any questions. I don't love that solution. I could ask you to do a bunch of work at home, give you, kind of an entire chapter to learn at home, and I might provide some kind of video support. I don't love that option either. I figure you probably have your plates full at this point. So my other alternative is to try and judiciously cut material from the course so that we cover well the things we're going to cover and we kind of leave out some of the other things. It's a little bit tricky to do because some of you will be going on to other courses that this is foundational for. So I am trying to be very careful looking at the prerequisites in this course, how it merges into future courses. So I'm keeping an eye on all of those things as I go through and thinking about what to keep and what to lose. We've covered most of the basics at this point for your foundational stuff for Physics 3500. Magnetism will be the next big topic that you will need for that course, so I'll make sure we kind of do the best we can on magnetism, so I am keeping an eye on that. If you have other concerns about other courses I haven't thought about, please let me know, because I don't want to leave out topics that kind of are going to be really important to you going forwards, but I am trying to keep an eye on it. I think that's all I wanted to say. Any questions? I think I covered everything. I've got a survey open on Brightspace where you can ask me questions. That one's anonymous in case you just want to ask things without having your name attached to it. So comments and concerns. I try to answer those on Brightspace as they come in. I think it was this class who asked about the pass-fail option. So maybe I will answer or address the pass-fail thing. This is a Twitter thread. Please don't laugh. I don't even know if young people use Twitter anymore. It does come from a reputable source. It comes from the Associate Dean of Curriculum in HSS, Humanities and Social Sciences. So the pass-fail option, the university says we encourage instructors to offer a pass-fail option. They can't mandate it. So I can only speak for this class. I can't speak for your other instructors. If one of you wants to consider a pass-fail option, I'm not going to make it blanket for the entire class. If it's something you want for yourself, come talk to me and we'll have a discussion. Pass-fail doesn't tend to be a super option, but it does have some value in some different situations. So kind of here's most of the description. I'm going to post this with the class notes too in case you want it for reference. So some places where it might be a good idea to take a pass over a numeric grade would be if you need a second year physics credit or a physics 2055 credit, but you don't necessarily have to get a good grade in it. So say you just need the credit for the class, but you don't have to have a minimum grade of 70 or 80 or whatever. And your grade in this class is not so hot, you're looking at passing with, I don't know, let's say a 52. So if that special circumstance applied to you, you might be better off taking a pass over a 52, because the 52 could bring down your GPA a little bit, which could have impacts on scholarships and other things like that. So that might be a situation where a pass would be preferable to a numeric grade. A case where a fail could be preferable to a numeric grade. These are also a little bit limited. First of all, one date I forgot to mention. The 10th of April is now the last day to drop classes. Along with being allowed to drop classes, you can get a full refund for your tuition for the course. So if on April 10th you want to drop, you can drop this class, no academic prejudice, and you get your money back. So for most people, if you anticipate a fail, and I hope that's not going to be anybody, but if you anticipate a fail in this course, it's probably in your best interest to drop it and get your money back. Do it again next year. Okay, so that's option number one if you think you're not going to pass. If you need to be registered in this course, and I know some programs have requirements that you have to be in a certain number of classes, whether you pass or fail, that has implications for visa status and things like that. So if you have to be registered, pass or fail, and you think you're going to fail it with a bad grade, say you're having a rough go of it, you've concentrated on other courses, you've completely let this one go, and you're going to come out with a 20% in this course. So say that applies to you, and you have to keep it for your status or whatever. It might be to your benefit to take a fail versus a numeric grade, because again, that very low grade will mess up your GPA. So there are some circumstances where a pass-fail could be benefit to you. I'm open to those things, but you just have to come talk to me because I won't assign it to anybody. My default is going to be to give you the numeric grade, so if you want pass-fail, we've got to talk about it. Okay. Does that bring up any questions? No, looks like we're all good. So why don't we start with our review of everything we've done so far. Okay, anybody recognize this? The show on TV, or was on TV. Oh. All right, so we'll leave that. So the first thing we started off with was largely review from Physics 1051, and we started with talking about electric fields around point charges. We used the specific example of an electric dipole, and we spent some time doing that. We know that electric field is a vector. It's the force per unit charge. Goes out of a positive into a negative. For a point charge, the field is kq over r squared. The force between 2 point charges, or a number of point charges, is given by Coulomb's law. F is K Q1 Q2 over R squared. Like charges repel, unlike charges attract. And then we used FET simulations off and on throughout the whole electric field portion. After we reviewed our point charges, we went on to continuous charge distributions. So what we said in this case was that a continuous charge distribution can be thought of as a whole bunch of little charges very close together to make a solid line of charge. We also looked at a ring and a plane and a disk. And we said to get the total electric field, you figure out what electric field does one charge make, and you draw that and you think about the components, and then you add them all up by doing the integral. So that's how we found our electric fields due to finite charge distributions. So there's our field around a plane, and we talked about the fact if we put two planes together, we get what's called a capacitor, and we'll spend lots of time on capacitors in this course. Then we did our Gauss's law section. Gauss's law says net electric flux, and flux is a scalar quantity that talks about how many electric field lines pass through an area. Net electric flux is given by the amount of charge inside the area we're talking about. That's the only thing it depends on. So we did flux. We applied Gauss's law to a line of charge, a solid cylinder, a sphere, both insulating and conducting, and a plane, and we applied that to a capacitor. So we did all those things with Gauss's law. And all these things that I'm showing here, they're from the little summary boxes I put up at the beginning of every class, or they're little caps of some slides we did. So all this is stuff you already have in your notes. Then we moved on to electric potential and electric potential energy. For electric potential energy, it's the negative of the work done by the electric field. So we use that idea to develop the idea of electric potential energy. For any 2 point charges, the electric potential energy is K Q1 Q2 over R. That's a scalar quantity, it can be positive or negative. Then the electric potential is the potential energy per unit charge. So if we put a charge in an area with potential, it will have potential energy. We used our ideas that we use with electric fields to find potentials of finite charge distributions. And again, we did the line, the ring, and the disk. So we did those things by thinking about one element of charge and then adding up the potential due to each element by doing the integral. We talked about the relationship between electric field and electric potential. Potential is the integral of the field. Field is the derivative of the potential. So we use that to sort of find one from the other. Given the field, we found the potential. Given the potential, we found the field. We also extended that to talk about equipotential lines, and we did a fair bit of that using our FET simulations. So we made some summaries and conclusions about those. And then the last topic we started to talk about was capacitors. We defined capacitance as a way to characterize capacitors. We introduced the idea of dielectrics, a material between two plates of a capacitor. And that's where we got to last time when we talked about how that changed the capacitance and the field between the plates and stuff like that. So that's everything we've done so far. Any questions? Okay, so I'm going to jump in today, and we're going to start with a capacitor example that hopefully will start to bring some stuff back. If stuff feels a bit fuzzy, then please just kind of stop me and ask some questions. And all those things I went through on the PowerPoint there, those are all going to get posted with the class notes. And I'm going to toss the new lab schedule in with those notes as well. Okay, here's our example. So this is going to be an example of a capacitor that looks like it's really tricky, but kind of when you get into it, it's not quite as hard as it seems to be. So for our capacitor, what we have is two concentric spherical conducting shells, and it's separated by a vacuum. So we have one shell, maybe like a bowling ball, and that's inside of another shell, say a bigger bowling ball. So we've got two shells separated from each other. If you're thinking about, well, how on earth would somebody build this spherical capacitor? You probably put like little ceramic pins separating the two layers. So some sort of insulator would just keep those in place, keep them from touching. But we don't kind of have to worry about that when we're just doing examples. So for our two shells, the inside shell has a total charge of plus Q, so this one is positive. It's got a radius from the center to the outside of that shell that we call RA. And the outer shell has a negative charge, minus Q. And the distance to the inside of that outer shell is RB. So this is positive, this is negative. There's going to be electric field going from the positive towards the negative. So there's a field between the two plates, two conducting plates with a field between it. That's a capacitor. Okay, so this just happens to be a spherical capacitor. So let's think about how we're going to find the capacitance. And let's start with the definition of capacitance. Capacitance is the charge divided by the potential difference. Okay, so that's where we'll start. That's not a tough place to start. The Q part is easy because that's given in the problem. The delta V, that's a little bit trickier, so let's see if we can figure out how do we find the potential difference between those two plates. So for our potential difference, delta V is going to be the potential at point A right here. Take away the potential at point B, take away the potential here. We want the difference in potential between those 2 points. Well, how are we going to find those two potentials? I'm not going to go through all the derivation, but I will remind us of the idea. So when we talked about potentials, we said that our potential delta V was negative the integral of E dot dr. And we applied this example to a spherical conductor to find the expression for the potential outside of a spherical conductor. We did this before. So what we can do is we'll just write down show steps. And when we work through the steps, we find that the potential outside of a spherical conductor is KQ over R, where Q is the charge inside the Gaussian surface that we were looking at when we did this problem. So our two surfaces that we'd be talking about, here's our first one at RA. So the potential at point A, VA, is K times Q divided by RA, because the only charge inside of that circle is the plus Q. The potential at point B is our potential right here, anywhere on this surface. And this is the inner surface of the outer shell. The potential at point B would be K times Q divided by RB, because the only charge inside that green circle is the plus Q. Okay, so we're only outside of that inner shell. So our potentials are going to be KQ over R. You okay here? All right, I'm trying to go through it a little bit slow because I'm just going to work on the premise that you were not studying Physics 2055 all of the time while I was on break. So that's kind of where I'm starting from here, is that probably you just put it aside and like read some books and stuff. Okay. So there's our idea of how we find our potential. Let's put these potentials in right here. Let's find our potential difference, put that in with our capacitor equation, and we'll find the capacitance of our capacitor. So VA minus VB is K times Q over RA, subtract K times Q over RB. Take our K and our Q outside. 1 over RA minus 1 over RB. You can leave it like that if you want. I sort of prefer to get a common denominator and add up the fractions. So for me, I take that one step further. KQ RB over RA RB minus RA over RA RB to get K times Q RB minus RA over RA RB. If this were a test and you stopped here, I wouldn't dock you any points. I just kind of like this form better, so that's why I went for that step. So there's our potential. Let's put that in with our capacitance and we'll have the problem done. So we've got Q over K times Q RB minus RA divided by RA, RB. Notice our Q's cancel, RA, RB over K, RB minus RA. So there's the capacitance for a spherical capacitor. Turns out to be kind of a simple result. Yeah.
Is there a way to use A epsilon naught by D instead of this?
Yeah, that's a good question. So if not everybody heard it, if we had our regular capacitor like this, then our capacitance is A epsilon naught over D. To me, this one gets a little complicated because the areas, they aren't quite the same as just the area of the plate. So maybe you could use it. I'll think about it a little bit and just see if that would apply. That's a good question. Any other questions? Okay. So the next thing we're going to get into is stuff you've been working on in the labs, and this is one slide that changed a little bit compared to what was previously posted. So when you have circuits, and this is just a video card that I asked John to take out of a computer for me. When you have circuits, they're full of capacitors, that's all these little round guys, and they're all connected to each other and the other circuit elements. So our next bit is to talk about the connections between capacitors in circuits, and then after we do this bit, we'll go into resistors, and then eventually inductors in circuits. So we're going to talk about how we connect those. I checked in with Edward in the labs, and he says you've been doing capacitors in series and parallel so far, so you kind of have an idea of what series and parallel are. So I'm going to sort of skim through the derivation for how we get the equation. For our capacitors in series, it just means that they're all joined in a row, they're all end to end. So we go straight from one capacitor into the next capacitor without any branching, so they're all in a line. That's a series connection. We'll use that idea with resistors as well. What we know about a series connector is that they all have to have the same charge. And to figure out that they have the same charge, we think about what happens when a charge leaves the battery. So a positive charge leaves the terminal of the battery, comes up here, comes around, hits the top plate right here. Once that charge hits right here, it can't go any further because it's at the top of a capacitor plate. It's essentially come to an end point. What can happen though is that because we have an extra positive charge on the top plate here, it's going to repel a positive charge away from the bottom plate. Physically, that's what's happening. So a positive charge is going to leave. The positive charge leaves, overall that plate becomes negative because a positive charge left. Okay, the positive hits this plate and it repels another positive. So this top plate is positive, the bottom is negative. We get down to this plate, that's a positive, that's a negative, and we come back around. That repeats over and over and over until the capacitors are all charged up and they all have exactly the same charge. So this is going to have charge Q, that has charge Q, that has charge Q. The other thing that happens in this circuit is that this battery supplies a total amount of potential delta V, and that total potential gets spread over the three capacitors. So if it puts out 10 volts, we'll get 10 volts altogether spread over those three capacitors, delta V1, delta V2, and delta V3. So that's what happens inside that circuit, that series circuit. For analysis, what we do is we draw what's called an equivalent circuit. And in an equivalent circuit, we take out these three capacitors, we put in one single capacitor that we call C equivalent, and the result is that this capacitor will carry charge Q when it's hooked up to the same battery. So that's what an equivalent circuit is when we have a series connection. So we take out these three, we put in the single one, we've got the same delta V, and we've got the same charge. So that's our series equivalent circuit. Because the potential is split over the three capacitors here, we can say that the total potential delta V is delta V1 plus delta V2 plus delta V3. Okay, so the total potential gets split over the three capacitors. Then we layer in that our potential is charge divided by capacitance. So Q over C equivalent. So if we say that delta V is Q over C equivalent for this circuit, that's going to be delta V1, which is going to be Q over C1 plus delta V2, Q over C2 plus delta V3, Q over C3. So then you notice you've got all your Q's on top, they cancel, you divide both sides by Q, and you're left with an expression for equivalent capacitance for capacitors in series. Okay. So if you have a set of capacitors in series, this is how you find the equivalent capacitance. Questions? And then the dot, dot, dot here is just because you do it for however many capacitors you have. If you had 100 capacitors, you would add up 100 of them. The next slide in the notes, I called it a homework question. So there's three capacitors. Find the equivalent capacitance, find the charge on and the potential across each capacitor. I'll leave that for homework, but I've got all the solutions done, so you'll be able to see that when I post the notes and compare your answers to it. So one connection is in series, the other connection is in parallel. So we'll look at that one next. So parallel capacitors are connected in a different way, and we say that those are connected kind of top to top and bottom to bottom. In a practical sense, if you had a capacitor down in the lab, you would hook it up to a battery, you take a lead off this end, hook it up to the top of the battery, a lead off this end, and hook it up to the bottom of the battery. So when you did that, the total potential over this capacitor C1 would be delta V, right? They're both hooked up directly to the battery. So C1 would have potential delta V, and it would carry an amount of charge Q1. Then for our second capacitor, we would take a new set of leads. We would hook one end up here to the top of the capacitor, the other to the battery. The other lead goes to the bottom of the capacitor, that goes to the bottom of the battery. Since this one is plugged directly into the battery, it also has potential delta V across it. Okay, so things in parallel have the same potential. So C2 carries delta V and the amount of charge Q2. Likewise, C3, that gets a set of leads hooked up straight to the battery. It has potential delta V and it has a charge Q3. So everything in parallel has the same potential across it. The amount of charge coming out of the battery, every time a charge comes out of the battery here, it comes up, comes to here, and then you'll see that it has a choice. The charge, as soon as it hits a branch, it can either go down or it can carry forwards. That tells us that the charge ends up splitting over the three capacitors. So every charge that comes out, it's going to go to one of the three capacitors. Right? So the charge has to split evenly over all of the capacitors. For this kind of circuit, we can also draw an equivalent. The equivalent is the same deal. We take out these three capacitors, we put in a single capacitor. This single capacitor will carry a charge delta V, and it will have a total charge of Q. Because that total charge is split over the three capacitors, we would say that the total charge Q is Q1 plus Q2 plus Q3. Okay, so the net charge is split or divided over the three capacitors. Q is C times V, so C equivalent times the potential delta V is C1 times delta V plus C2 times delta V plus C3 times delta V. The delta V's are all the same because they're all in parallel, so you can divide both sides by delta V. And what you're left with is an expression for the equivalent capacitance for a set of capacitors in parallel. The place I would caution you here, and this would happen if you remember your high school physics or your 1051 physics pretty well. Capacitors in series and parallel are kind of the opposite of resistors in series and parallel. So when you're doing your homework, it's fine. You're not going to get those equations mixed up. But if you're in a test, you might just be working a little bit too fast and you might get them confused. So make sure when you're doing a problem, you just take a breath. Remember, is this a capacitor or a resistor, and how do I add them up? Because it's not the same for both of them. Okay, just like the series one, I've got a homework one for parallel. Find the net capacitance and what is the charge. So we'll do one a little bit more interesting in class. So when we look at these boards, if you work through the connectors on all these, it turns out, for the most part, they're not all connected in series, or they're not all connected in parallel. It tends to be more complicated. Some are series, some are parallel. So mostly you end up with combination circuits. And that's what this picture is here. This is a combination circuit. So some stuff is parallel, some stuff is series. And we can still analyze it, but we have to be careful and do it step by step, dealing with the parallel and series bits as we go. So for this system of capacitors, C1 and C2 are right here, C3 is right here, and we want to find the equivalent capacitance. So when you do these, the place to start is by looking at the diagram and asking, can I see anywhere where this is obviously in series or obviously in parallel? So I'm going to start with the series connections because I think those are really easy to see. The series are when they're all in a row, they're connected in a line. So if I come out of the battery and I come to here, that's fine. This one comes up to here and then it branches. So this one is not connected straight in a line to either one of these two. And these are not straight in a line to each other. So nothing here is directly in series. Okay, so we're not going to start with a series connection. What about a parallel connection? So parallel is top to top, bottom to bottom. So if we go out of the tops of C1 and C2, they join up right here. If we go out of the bottoms, they join up right here. So these are connected top to top and bottom to bottom. So C1 and C2 are connected in parallel. So we can find the C equivalent, and I'll just put a P on it for C equivalent parallel. To get the equivalent capacitance of two capacitors in parallel, we just add them up, C1 plus C2. 4 microfarads plus 12 microfarads to get 16 microfarads. After you do an equivalent branch like this, the next thing you do is redraw your circuit, you put in that equivalency, and then you go to the next step in your simplification. So I'm going to redraw this circuit. I'm going to take out C1 and C2, and I'm going to put in this equivalence. So redraw. I've got my battery here. C equivalent parallel here. C3 here. So now I look at this picture and I ask, is there an obvious connection here? When I look at these, I come out of my battery and come to C3. My next step is to come to C equivalent parallel. Those are right in a row, there's no branching there. Those two are in series, so I can find an equivalence of those guys by adding them in series. So 1 over C equivalent is going to be 1 over C equivalent parallel plus 1 over C3. 1 over 16 microfarads plus 1 over 6 microfarads. If you're a calculator sort of person, you're probably just going to do this on your calculator. If you're a fraction sort of person, you're going to do this as a fractional addition. So 16 is the same as 3 over 48. 6 is the same as 8 over 40, or 1 over 6 is the same as 8 over 48. So we get 11 over 48 microfarads for my 1 over C equivalent. Then to get my C equivalent, I just take the inverse of both sides. Which is 4.36 microfarads. And then just to finish things nicely, we'll redraw it once more, and we'll label that in our answer. Okay, any questions to here? Yeah.
Why, when you first put the parallel together, like you wrote CEQ, like comma P, what does that P?
Oh, just because these two are in parallel, I didn't want to have two CEQs floating around. I just put the P in there
Yeah,
to
I just wondering what the
keep them apart. Yeah. So that's the first part of our question done. Find the equivalent capacitance of the system shown. The next bit says find the potential across and the charge on capacitor C3. So for this one, we have to start working backwards, remembering things in series have the same charge, things in parallel have the same potential. So what we want to do in this sort of a problem, find the potential across a capacitor that's up here, is we have to see what we know about this system, and then we have to trace it backwards to the previous step. So I'm going to start with this circuit, and I'm going to see what can I learn about this circuit. So I know my equivalent capacitance, and I know my potential is 12 volts. If I know C and I know delta V, I can find my charge. So my charge and my equivalent capacitance Q is C equivalent times delta V, 4.36 microfarads times 12 volts to get a charge of 52.4 microcoulombs. You can leave it in micro, or you can write 52.4 times 10 to the minus 6 coulombs. Doesn't matter, whichever you prefer. It all means the same thing. So then the next thing we have to do is ask, how does this charge, how does this tell us what the charge is on capacitor C3? Right, so that's our next bit. So we have to remember here that CEQ is the series equivalent of C3 and that parallel combination that we already found. If it's the series equivalent, they have the same charge. So series means same charge. So C3 also carries charge Q. Because it's a series equivalent. If we know the capacitance C3, 6 microfarads, and the charge on it, 52.4 microcoulombs, if we know charge and capacitance, we can find the potential. So delta V3 is Q divided by C3. That potential turns out to be 8.73 volts. When we get to this answer, the potential across this capacitor, hopefully we'll notice that the potential across this capacitor is less than the total potential, and that's a good thing, right? Because the potential 12 volts, it gets split over everything, so the potential on any one capacitor should be smaller than the total potential. So this is in line with what we expected. If it was bigger, you'd go back and you'd check your math and see if you made a mistake somewhere in your calculation. Okay, questions? Okay, so let's do another one. So this was a new example I added to this chapter. You would like to add a second capacitor to a 24 microfarad capacitor to obtain an equivalent capacitance of 15 microfarads. So what's happening here is that you want to put in a second capacitor. Let's call this one C2. You want to attach that to an existing capacitor, C1, and you want the equivalent capacitance to be 15 microfarads. So our first question is, should we hook it up in series or should we hook it up in parallel? Okay, I'm going to write down the two equations for series and parallel, and I want you to think about the answer, and after I write down the questions, we'll see what you come up with. Okay, so thoughts? Should we connect it in series or parallel? Series. So first answer that got said out loud was series. Who agrees with series? Okay, anybody like to justify why it's in series?
If it's connected in parallel, then the total capacitance will increase rather than decrease to 15.
Okay, super answer, and it's exactly the way I think of it as well. When we hook them up in parallel, they get bigger. This one is smaller, so it can't be connected in parallel. It has to be in series. So we'll call this one wrong, and this one right, because CEQ is less than C1. Okay, so there's our answer and our reason. So part B, find the value of C2. We'll write down the equation again. So we're trying to find C2, so we'll put 1 over C2 on one side, the other stuff on the other side. So 1 over C equivalent is 1 over 15 microfarads minus 1 over 24 microfarads. Again, you can go fractions or calculator, it doesn't really matter. 1 over 15 is the same as 8 over 120. 1 over 24 is 5 over 120. So we get 3 over 120 microfarads. Take the inverse of both sides, and C2 is 120 microfarads over 3, or 40 microfarads. Okay, any questions? I have one more example that I want to do about these connecting capacitors. But like we only have 7 minutes left, and I don't want to rush, and I don't want to stop in the middle with break coming up. So let's quit here. I'm not planning to give you any work over break. I expect some of your other courses might be piling up, and if they're not, then you certainly deserve to take a proper break. So we'll be back kind of Monday the 20th, and we'll pick up there.